So maybe a warm hello to Professor Villegas. I was a postdoc at ICTP in 2013.
Ah, okay. Yes, I recognize you, but you change. You change your beard, or you always have a beard?
Maybe maybe I didn't have the beard then. Yeah.
Okay.
But otherwise, it's the same.
It's still the same.
You should visit India, Professor Villegas, sometime.
Oh, I would love to. I was in India once and I enjoyed it very much.
Okay.
I would love to, but I have some health issues, so very long flights are a bit of a problem, but maybe.
I see. I see.
Or maybe you start the recording and we start. Sudarshan, you can start.
Okay, so pleasure to introduce, to welcome Professor Villegas again for his second talk on hypergeometric motives. Professor Villegas.
Okay, so thank you, and thank you everybody for coming back. Let me recap where we were. So I'm now going to zoom in a bit more in specifics. So the starting point for defining these objects, which I might call the hypergeometric data, after some various transformations, I will give it in the following form. This is the most convenient. So we have two polynomials with integer coefficients of same degree, let's say n, and they have only roots of unity as roots. And they're relatively prime. Okay. These, remind you, are going to be the characteristic polynomials of these local monodromies that come from the differential equation as you analytically continue solutions. In fact, a second completely equivalent form of giving this data, which in fact I will use more than the previous one, is since the roots of these polynomials are roots of unity, we can rewrite the quotient as a product ratio rather of simple factors like this, where we can pick these integers to be in non-decreasing order, since the order of them doesn't matter. And we'll see that the condition, since the q infinity and q0 have the same degree, the sum of the gammas is 0. And we do this economically, so neither gamma I nor gamma I plus gamma j is 0. So we don't have cancellations. And we'll typically write gamma as a string of these numbers. So running an example, that was the Legendre family. In this format consists of this vector. Okay, so this is the starting point. Now I want to define what this hypergeometric motive is. And for a while, this was somewhat of a bit of a hand-wavy thing. And it took a little bit of time to make a precise definition, which I'll try to sketch. So following GKZ, perhaps we're the first to consider this family of hypersurfaces of a torus, of a product of C stars. These are going to be D in number, and D is the length minus 2. So it's going to be a little tedious to give this, but I want to give the precise definition. So L is the number of gammas, which is a somewhat erratic kind of invariant. So for example, for the running example, L is a 6. And as we'll see, the dimension of this variety, well, as I'm defining it, is a hypersurface in this L-2 dimensional product of C stars. So itself is of dimension L-3. So for the running example of the Legendre family, already in which typically is sort of the simplest, or at least the nicest example to discuss, we have elliptic curves, but in this format, what we're going to assign to this data is actually threefold. So it looks a little bit going the wrong way, but this has the beauty that is completely systematic. So there's no not a whole lot of choices to make out of this gamma. I'm going to write down a specific concrete family of hypersurfaces of this torus. And the way we do this is there's going to be a parameter. So it's a family, one parameter family. And it's given by one equation, which let me write it down. So we're going to pick monomials, Mi. I think I wrote this last time, but it's a reminder. So Mi is these monomials with exponents, integer exponents in Z to the D. And the key thing here is that they are orthogonal to gamma. So there's going to be certainly a choice, but we want to pick them in this sort of most economical way. And so for that, we can state it as saying that these monomials affinely generate the lattice Z to the D. And then there is this kappa, these Ks. I didn't say it, but I will always assume these gammas are relatively prime. So I can find a linear combination of them that is 1. Okay, so this again is a bit perhaps too much detail for that you may want to see, but my point is that it's completely explicit. And
excuse me, what
yeah?
does affinely generate?
Well, I mean, you can in practice you can say, okay, I subtract one of the vectors, so and then I get one of them is, so subtract from the L, subtract one of them to all of them. One of them is 0, so throw that one away.
Okay.
And then the remaining ones, you want them to span the lattice.
Okay, thank you.
Yeah. So another way to think of this is that, so an object that plays quite an important role in this whole discussion is the convex hull of these monomials. And I'll draw a picture of an example in a second. So you have plenty of choices, but there's two things somehow involved. You can pick your MDs sort of without thinking too much, and they will produce a huge polytope, and so you can find ones that have a smaller polytope. So you can look for the smallest possible volume, and even within that, you can change them around with a affine invertible transformation over Z, but that is going to change the equation, of course, but not change the variety in its isomorphism class. But I do want the volume to be the smaller, so that's equivalent to this spanning. So another way to think of it is you pick them as tightly as possible. So, for example, another family of elliptic curves, but from this point of view, a little bit better behaved, would be to consider this vector, gamma, and then a simple choice. So L here is 4, so the ambient dimension is 2, 4 minus 2, and you can pick. I don't think you. I mean, I'm doing things so precise you can put them in a computer. You probably don't want to see that necessarily, but anyway, here's a choice. And if you look at the polytope, which in this case is a polygon, it will be with this choice with this, and you could pick. You could have picked something which gives you, for example, this polygon, and so this would be a choice that satisfies everything other than the spanning condition. So this would be something of volume area bigger than that one. So this we don't pick, this one we want. Okay, so the hypergeometric motive then that we associate to this data, let me say it in words, but it takes a bit of work to make precise what that means. So it's somewhat a bittersweet situation, because to explain it will take a bit of time. So what we have is this variety, and this variety that I'm thinking here is an affine variety. It's certainly not going to be projective, compact in general. So, but still it has so I'll use the notation that I'm using in the paper, and we maybe have too many letters, but it's convenient. So let me call kappa the dimension of this thing. So it's L minus 3. So we can look at the cohomology of this variety, the middle cohomology. And so I'll say very quickly and in words without getting into too much detail, because it will require a lot of work. But this, since it's an affine, a non-projective variety, is typically going to be smooth away from in fact 3 points. So smoothness is not an issue, but it's not compact. So it has a cohomology, and this cohomology has a mixostructure. Again, I'm just going to quickly just say this without getting into too much technical detail. This mixostructure has in particular, this cohomology has pieces of various weights, and the hypergeometric motive is by definition the weight kappa piece. And there's a further thing that I need to do. I'll say a little bit more about this a little later, but you you really have to also remove the contribution from the ambient torus, and so that is this P that stands for primitive cohomology. But anyway, if all of this is new to you, don't worry. I mean, what I try to say is that there is a specific concrete definition of what this motive is. Okay. Now, I'm going to go back now to arithmetic. And what we would like to do, because of this motivic existence, there is a corresponding arithmetic
Please
picture.
recall what happens when the D
Sorry?
equals 1.
Excuse me?
Please recall what happens when D equals 1.
When D equals 1, yeah, that's not a bad situation. D equals 1. What we have
Here's,
is,
what is this? Then K is 0.
then yes, this kappa is 0. So what we have is a
So the mixed order structure is
going to be a weight 0.
weight
So in fact, those are interesting cases. So D equals 1. What we have is we're going to have L is L is 3. So there's three dots, and there's 3 monomials in Z. And so the equation Z mu is going to be a trinomial in one variable. And in fact, it's something that goes way back and is rediscovered periodically, that the solutions to a trinomial equation are given by hypergeometric series. Well, basically, I mean, you have to do some change of variables possibly. But anyway, you can describe the solutions to a one variable trinomial equation in terms of hypergeometric series. And in fact, this is true for any degree, any number of monomials. But then you need hypergeometric series with more variables. That's a result
the work of Schwartz. I think last time we spoke, it's not Hurwitz, but Schwartz.
Okay. Yeah. Well, Schwartz, of course, was the first to prove a classification of hypergeometric series of rank 2, the standard Gauss type hypergeometrics, when those were algebraic. And that was the starting point for a lot of other work, culminating with Villegas and Heckman, which did this for any number of any order differential equation. Yeah, so I take to mean, I like to think of things that happened before as often have a new sort of interpretation, motivic interpretation. What Schwartz was doing, if you like, is to classify rank 2 hypergeometric motives of weight 0. Weight 0 would be equivalent to algebraic or finite monodrome. Okay, so yeah, so these trinomial equations are actually quite interesting. Clearly, you can just describe them with not a whole lot. I mean, you just need these 3 integers, and you can normalize them to be these belly polynomials. So so you can consider these where C is A plus B. These correspond precisely to gamma equal to minus C A plus A comma B. So in the setting that I'm considering A, B equal prime. So these are examples where you can write down very explicitly what is the equation, and it yeah, so it's a dimension 0, and it also corresponds to weight 0. So the difficulty, or the somehow you have to, you never, there's no free lunch, right? I mean, so if you motive somehow, I'll discuss this a bit more later. I mean, if this motive, for example, here is a curve, so we know it's somehow naturally a curve, but if you go through this machinery, you get a threefold. So it happens that the variety you can write down may end up having a dimension much bigger than what you could have expected. Okay, so now, so go back to the Legendre curve. Just to connect to the arithmetic, I particularly like this story. I mean, Doring proved that if you count the number of points on your Legendre curve over a finite field, say Fp, then modulo P, and if you've never seen this before, I recommend you try it. I mean, it's a beautiful, nice exercise to do this calculation. You can see that you can explicitly write down what the number of points is modulo P. So modulo P, in terms of a polynomial, but lo and behold, is pretty much the same thing as the series that gives us a period that we started with. So, but concretely, it's a polynomial. You truncate it to order p minus 1 over 2, but it's the same coefficients. And then you show that the number of points of the curve has this property. Now, so Iguza noticed something quite remarkable, that in fact, the polynomial on the right-hand side satisfies the same differential equation, but now mod P as the period function F. And this, of course, is the starting point for much of the amazing work that Dwork did, connecting differential equations with counting points, and his proof of rationality of the zeta function. Now, this only gives us a connection that is mod P, but this can be souped up to an actual p-adic formula. So this number of points, we wrote it as p plus 1 minus 8p, and depends on the choice of parameter. So here, of course, we better have that we choose t to be an fp to make sense of this. So it's a formula that reduces to this one mod p, and I'll write it in somewhat condensed form without making too explicit. It's a sum over characters of fp star to c star, or maybe, yeah, we can do it over the complex numbers. And these j's are some Jacobi sums, which are products of Gauss sums. So if you want to put this in a computer, you better be precise, but I don't think we need it. So there's a way to take the data that defines our hypergeometric motive and build these Jacobi sums that are going to be coefficients of a sum, which gives us this AP of T. In general, gives the trace of Frobenius. This is and we can do this for any power of P. So let me try to explain a little bit what this means. This is for all but finally many P. So for elliptic curves, or say for the Legendre curve, you probably will not use this formula. There's much better ways of computing this if you want to do this in practice. But the beauty is that this is a completely generic expression that you can apply to all kinds of cases where it would be very difficult possibly to get a hold of these numbers in a different way. And it also, it's actually quite computable. And I'll show you examples of this in a second using what was implemented at Magma. Much of this work started in fact in 2009 and in a workshop that we had in Spain, and Henri Cohen was fortunately there, and he did a lot of the very sophisticated programming to get something like this to be usable in a very efficient way. Okay. So let me try to explain this issue of the Frobenius very, very superficially, just to at least tell you what we get at the end of the day and why is that of interest. So given the data, the Q infinity and Q0, and a choice of T, a parameter, because these are families, and let's stay away from 0 and 1, which are singular. They give rise to this motive. Whatever that is an object that has both a sort of complex life and an arithmetic life. And the arithmetic life is one in which for all but finally many primes, we get an automorphism, this Frobenius, acting on a vector space, which is technically an elliptic vector space, but let's say call it V of dimension n, which is the common degree of the polynomials. And with which we can produce an Euler factor in this way. So this automorphism acts on the vector space and has a characteristic polynomial, or sort of inverse characteristic polynomial, if you like, written in this manner. This is a polynomial of degree n, the dimension of the space. And the way one can compute it is, as you probably know, you can compute the characteristic polynomial of a linear map if you know the successive traces of its powers. If you have n traces, the powers of the first n powers of your automorphism, you can, by the Newton formulas, compute the characteristic polynomial. So that's how one can get this polynomial from this formula. There is a similar formula to this one that will compute the traces. So this is the trace of Frobenius, power 1, and higher powers of Frobenius will be a correspondingly similar formula where now you run over characters of fp to the r if you want the rth trace, the trace of the rth power. So anyway, at the end of the day, what happens is you produce this Euler factor, which is the Euler factor of an L series, which is the L series of this motive. And here I'm putting all the primes. So there's some further complicated work to do to make sense of this for the primes P that were excluded from the previous discussion. And when you want to do this in practice, this is one of the major headaches of how to get those. But we'll march on.
Isn't it LP inverse?
It is LP inverse, thank you. Yes, thank you. Okay. Now, what do we expect from this? Why do we care about this L function? Well, a lot of things are expected to one be able to reap benefits from having constructed this thing. But at the very least, this is a L function that behaves like what L functions should behave like, which is that if you add to it a term that comes from sort of the infinity prime, if you like, then it should have an analytic continuation and a functional equation. So let me make some comments about this. The expectation this is about motives in general, not about the hypergeometric ones. The point about hypergeometric ones is that you can test this for quite efficiently for a whole lot of situations where it would be hard to get these L functions otherwise. So let me explain these various things I wrote down. So W here is an integer, positive integer, non-negative integer, called the weight of this motive H. So non-negative integer. And it appears both in the L function in the presumed functional equation, but also in the nature of this Euler factor. The inverse roots of this polynomial have absolute value P to the W over 2. And this, when we talk about the L function coming from a smooth projective variety, this is what part of the Weil conjectures that Deli improved, and this would be the analog of the Riemann hypothesis for things over a finite field. Okay, then what's gamma infinity? This is a product of factors of the form gamma s minus j, or maybe gamma s minus j over 2 for integers j. So it's a product of standard gamma factors, translated gamma factors. And I'll come back to this because this is an important piece of this story. And N,
is there no power of pi also?
yeah, it's kind of buried in there. So there is a power of pi, which I'll put powers of pi. Yeah, I didn't want to make it too precise because I'm gonna bog down with the details. So, but indeed, there is some power of pi. Okay, and then there's this number n bigger or equal to 1, which is the conductor. So if you're familiar with elliptic curves, all of this would sound familiar because it does extend that. And the point of this number is that in particular is divisible only by the primes that we have excluded in the previous discussion. So it's some sort of measure of how bad things are for certain primes. Okay, so I thought I'll show you an example of this by looking at magma. So let's see if I can manage to do this. So I'm going to take a motive defined as follows. I take alpha to be a half, 4 times, and beta to be 0, 0, 0, 0. And I take t, initially I'll take it to be t, some random number. 7/11 seems random enough. And I want to show you how what happens with the calculations with magma. So let me see if I'm still on there. Yeah. So I'll show you my screen now with magma. Hope this is right. Okay, can you see some black screen
Yes,
with
yes.
Okay. So I'm going to define. So in part, I want to do a little advertising for what Mark has done. I mean, as I mentioned, a lot of it originally was done by Henri Cohen as well, but this was the implementation in magma of those ideas, plus some further work. So I just defined the motive H, and you can put in the data in various formats. I just chose the one I just gave. So in terms of the alphas and the betas. Now I compute the L series, and it tells us that the wild prime information, so there are primes that are need the special care, as we were discussing, and is making some guesses as to what happens to them. So some of these guesses took quite a bit of work to get to the point to be able to guess them, and they are not necessarily proven to be correct, but they work in the sense that you can check, as we'll do in a second, the functional equation and see that in fact they do seem to satisfy the expected behavior. So here I'm just going to compute the Euler factor for the prime 5. Sorry?
Sorry, what am I supposed to see? Right now I see a black screen with a white stripe in the middle.
Oh, you don't see what I'm writing?
No.
No.
Okay. Well, that was not good. Let me try again. maybe it's this. Yeah, maybe it's this. Do you see some numbers now?
Yeah.
Yeah.
Yeah, now it is coming. What you
Okay, so I was typing things you didn't see. So let me see if you agree. You see my cursor moving?
Yeah, yeah.
Okay, so here's age. I'm defining it in terms of the alphas and the betas. Yeah. Here's the L function of age with the second argument is the value of t, little t,
Okay.
the parameter.
Yes.
And it tells, yeah.
Yeah.
And it tells me that Magma is making some guesses as to what happens with the bi primes.
All right.
Okay, and then I just computed the Euler factor for this situation for the prime 5.
Mm-hmm. Okay.
Okay, so
so there's a lot hidden.
There's a lot of hidden, yes, indeed. But what it's doing is computing these traces the way we said, by using these formulas with the characters and the Jacobi sums and so on. But all of that is sort of, yeah, under the hood. So I just want to look at the roots of this polynomial. And then let me see what the absolute value of the square of one of these roots is 125. So what this tells us is, I could look at all the other roots as well. They will all have the same absolute value. There's 4 of them. So this is the weight story of the Weil conjectures. And so the weight here is 3, 5 cubed is 125. And we can check. So the weight is something that is purely combinatorial from the data. And you can compute, so independently of doing anything with Euler factors, you can compute the weight of this motive. And so let's see what is the conductor of this L series. So this is a humongous conductor. It has the bad prime factors are 2, 7, and 11. And so if I compute the Euler factors at 2 and 7 and 11, I cannot at least immediately use the formula that I wrote down. And so Magma is making some guesses that the factor for 2 is 1. This factor for 7 is also 1. And factor 11 is also, well, not quite, -1. So it's a degree 1. So this needs extra special attention. And as I said, this was, in a way, a lot of the work that we've done over the years is to get to the point to be able to at least make a good guess for what these things are. All right, so let me just do one last thing, which is the conductor of that choice of little t is way too big to do much else. So let me change the conductor to something smaller. So I pick little t to be 2 to the -8. And now if we compute the conductor of this new L series, we see that is in fact 255. It only involves these primes 3, 5, and 17. So this is much more amenable to calculations. And this is also buried under the hood that there is, in fact, a fairly robust way to test whether something you think satisfies a functional equation of the nature that we wrote down actually seems to do so numerically. And this is what this CFE nu stands for, check functional equation nu of this L. And that this comes out to be 0, 0, 0, 0, 0. It's not a proof, of course, but a fairly strong indication that this choice this L function that we constructed with all the various extra things that were guessed actually seems to satisfy the correct functional equation. Now, I remember as an anecdote, I gave this talk before, or mentioned this fact before, and I remember a story of John Tate that he was checking some conjecture in his computer, and he had a list of numbers that were coming out, 1 and -1, and they were matching. In each column, the same number was appearing in both columns, so he was very happy. His conjecture seemed to be correct. And he showed this to his wife. He was very excited, and his wife just looked at it and said, well, I can do that too. So, you know, it's easy to print out all these zeros, but you have to believe me that I did not make them up. I mean, the computer actually calculated them. Anyway, this is sort of an invitation for you to play with this, to this magma package, which is quite interesting, and to I don't know sorry.
I'm just wondering, how did you know to choose that particular T, which was
that's a good point. We have so roughly speaking, the primes that are bad, let's say for that example, is certainly 2 because it is in a denominator of one of the alphas and the betas. Those are going to be really bad. And then you also have primes that have to do with your choice of T, and that are going to be the primes that appear both in T and in 1 - T. And so you can choose it so that those appearing there are few, and there's also the fact that they appear there doesn't guarantee that they will be bad. They could be somehow miraculously disappear if they have the right exponent. So you have to play a game with T and 1 - T.
Other questions? Are there bounds on the exponents at the bad prime?
We have a guess, which is I think one of the most interesting things still pending in my view, because it could potentially be interesting for other situations. So we do have a guess for the exponent of any given prime in the conductor. Yes, but yeah. Okay, so so what I have left of time, I want to say a little bit about the gamma infinity, which was this product of pi's and gammas. So what goes into this is this is determined by geometric invariants called Hodge numbers. And I will just give a very, very sort of superficial description what this is. And they initially are invariants of a complex manifold, an algebraic manifold, to be more careful, say X. So we have cohomology groups of these manifolds, and it is a theorem of Hodge that if you look at the complexification of these spaces, so tensor raised to scalars to C, then they have a decomposition into pieces indexed by two indices I and j that add up to k, k being the order of the cohomology. So roughly speaking, hk corresponds to k differential forms, and the I and j have to do with how many sort of dz's there are and how many dz bars there are when you write that differential form in complex coordinates. So these are invariants of this algebraic or Kähler. This is these manifolds, and they're important invariants. And what we're going to keep from them is their dimension of the corresponding subspace. So these are these Hodge numbers, and it's convenient to package them into one vector, which I'll just call H. And for us, the only case that will matter will be exactly when this K is kappa, the dimension of the variety that we were discussing before. So we start with HK0, HK minus 1, 1, up to H1, K minus 1, H0, K, all kappa. Now, so just put them in an array. So what do we know about these numbers? For a complex, smooth complex manifold, we know they are symmetric. The sum of them is the total dimension, which is the dimension of the cohomology, which is what's called the Betti number, the kth Betti number. So these numbers are sort of a refinement of this Betti number. So let me give you an example. So if you take X to be a smooth cubic fourfold, so it's a hypersurface in P5 that is the zero locus of some cubic, homogeneous cubic polynomial, then any such X has Hodge numbers of the form 0, 1, 21, 1, 0. Okay. Sort of a curve of genus G, for comparison, has so this is always in the middle cohomology. So being dimension 1, there'll be H1. The H is simply G, comma G. So notice that the length of this vector is one more than the cohomology index. Okay, now there's two things that we should consider about these numbers. First is that if you have X a hypersurface in projective space where kappa is even, then there is a decomposition of this cohomology into a codimension 1 piece and a one-dimensional piece. This is 1, and this is sort of Betti K minus 1. So, in other words, there is a natural factor in there that you might as well forget. And then the other thing is that it could be the case as we have for the fourfold, that there are these zeros outside. And these exterior zeros in H can be removed by what's called a Tate twist. In the sense that you can consider an object, if you like, that has the same Hodge numbers, but where the zeros have been removed. Okay, so for example, in this cubic fourfold, there is a one-dimensional piece that comes from this and this decomposition. So we can take away this one that comes from this extra one-dimensional factor that comes from the fact that you can intersect a variety with a hyperplane. And that gives you a class that will span this one-dimensional subspace. And on the other hand, once we have that, we can also remove the individual exterior zeros. So we end up with something that looks like 121, which looks like H2 of a surface. So that's one thing that once you start playing these games, you come to realize that these objects kind of can migrate and be living in different cohomologies. So you can hope for. So what this is saying is that if you look at the H4 of a cubic fourfold, you could hope to find a surface that has the same motive in H4 of the fourfold, but that comes from a surface that has been sort of promoted by the Tate twist to live in the fourfold. And this is the kind of thing that happens all the time. And that's what I was saying, is that even in the case, for example, of the Legendre elliptic curve, the way this whole setup will make it appear is not as an elliptic curve, but as having been promoted to live in a H3 of a threefold. And that's just the way it is. And it seems often very difficult to even if you know that it sort of naturally comes from, say, a curve, to actually go from the high dimensional variety that this procedure gives you to the actual family of curves. But from the point of view of motives, the thing is sitting there just as well as it did in a curve, even if you couldn't find it, and you can operate and do calculations with it just as well as if you had a curve. So I'll end with just one fact. So these Hodge numbers are quite a way to organize all this enormous zoo of these hypergeometric motives. I don't know if I convey this enough, that the amount of data you need to define them is very, very little. And so there's just enormous amount of choices. And so to classify them according to Hodge vectors is a way to give some order to this whole zoo. So for example, one thing that happens is that for every rank less or equal to 19, you could just check this by brute force. Every Hodge vector which is sort of symmetric So potential Hodge vector, symmetric, with no interior zeros, because those will not ever appear in a family, is realizable as a hypergeometric motive. And this is just a calculation. It took quite a while because the amount of data is pretty substantial, but it's just a verification that every single Hodge vector that could potentially come from some motive, in fact, does. A motive that sort of in a non-trivial way, so irreducible motive in a family. But once you pass 19, there are some examples where it doesn't occur. So it's sort of an inverse analog of a sort of inverse Hodge problem, which is if I give you potential Hodge vector, is there a motive defined over Q that has that realizes it? And I think not a whole lot is known about it. And these hypergeometric motives are wide enough; they seem to cover a whole range of possibilities, at least if the rank is not too big. So I'll finish with this fact that if in rank 24, just to give you a sense of what the zoo looks like, in rank 24, for reasons that I cannot explain, just because the calculation tells us is the case, in rank 24, this is not realizable. So there is no hypergeometric motive with this very unusual Hodge vector. But if you look at this one, then is realized 9,905,208 families of AGMs. So the disparity is really shocking, and I have not a whole lot of understanding. So some particular Hodge vectors seem to be extremely popular, and some seem to be non-existent. In this world of hypergeometric motives, it will be, I think I would kind of willing to bet it would be almost impossible to produce something with this Hodge vector in any other way. I certainly would not know how to do it. If you look at the standard things like hypersurfaces, complete intersections, and so on, you'll see that the Hodge vectors are very, very sparse. They kind of cover a very small part of the space of possibilities. So this is one interesting feature of the hypergeometric motives, is that they do seem to cover a lot of ground, at least again, if the rank is not too big. And with that, I think I should stop here. Thank you.
So, let's thank Professor Villegas for a very nice talk. Are there any questions?
Since you mentioned it, I would like to ask that Hodge vector that you have written down, does this give Hodge numbers for some pure motive, maybe not a hypergeometric motive?
Which one? The last one here?
The last one, 9112119.
I don't know. So one thing I can tell you, if you look at the data, you know, I always follow my mentor Don Sagi's advice that once you spend as much time looking at the result of an experiment as you did as preparing or running it. So one thing that comes, if you look at the full data, comes out quite clearly, is that these numbers, 9112 and so on, seem to be, what's the word, U-shaped. Is that convex? Whereas the one that does appear a lot is concave. So there seems to be some tendency to these Hodge vectors to be of the latter kind. but this is, you know, and there may be interesting geometric reasons for this to happen, but it's all a bit of a speculation. But to answer your concrete question, I don't know how to realize this in any other way, in no way. Yeah.
Thank you for a very nice talk. Thank you.
Thank you.
Are there any other questions?
I have a question. It's about modularity. I'm aware, of course, of what has been done between Dave Roberts and Chris Poore and Dave Ewan, but are there other, and also, what's his name? I'm aware of one other case, but is that pretty much all that has been done on modularity of these hypergeometric motives?
I think so. I mean, I think I know probably as much as you do. Yeah, I think there was quite a bit of interest in Hodge vectors 1, 1, 1, 1, sort of the kind of thing that that appears in Calabi-Yau in mirror symmetry and so on, with SP4 or the paramodular SP4s. Other than that, I'm not aware of other things. I mean, yeah. No, it's the thing is, as you, I'm sure you know much better than me. I mean, once you go past GL2, the eigenvalues for Venus are only a small fraction of what these automorphic forms know about. So finding them is a much bigger proposition than the object that you started with.
Thank you.
Any more questions? Then maybe let's thank Professor Villegas once again for a very nice talk.
Thank you everybody for being here.
Thanks, Sudarshan, for sharing this also. And thanks, Professor. We'll
Thank
see you again.
Yep.
Bye.
Bye now.
Have a nice day. Pawan, you can stop the things. In the meeting in the live stream also, YouTube studio.